Welcome to AI and Machine Learning Deep Dives. I'm really excited about today's topic because we're taking a deep dive into a core concept that, well, it often feels a bit slippery, even for those of us who work with these models regularly. We're talking about what exactly are support vectors within the world of support vector machines, or SVMs. It's a term you hear constantly, but getting to its precise meaning can sometimes be a real challenge.
That's absolutely right. I mean, many people grasp SVMs at a high level, this idea of finding the best boundary, the best line or plane to separate data points into different categories.
Hmm.
But I find that truly understanding how these powerful models work under the hood, and crucially, why they are so efficient, well, it really hinges entirely on those specific data points we call support vectors.
Okay.
So yeah, we're going to unpack this concept for you today, starting with the intuitive idea, and then moving into the, let's say, the precise mathematical definition that really brings it all together. Ready to dig in?
Okay, I'm ready. Let's unpack this for you.
Yeah.
So when we talk about a support vector machine, the main goal often is to find what we call an optimal separating hyperplane.
Mm.
Now think of it this way. Imagine you've got a bunch of data points scattered on a graph, maybe representing two different classes, like spam emails versus not spam.
Right.
The optimal separating hyperplane is basically just the very best decision boundary. Could be a line in 2D, a plane in 3D, or something more complex in higher
The
dimensions
hyperplane, yeah.
that divides these data points into their different classes with the widest possible gap between them. We're trying to maximize that separation, give ourselves the most confidence.
Exactly. And that gap you just mentioned,
Yeah.
that's what we call the margin. Now, in the sort of, the simplest case,
Right, the ideal scenario.
where your data is what we call linearly separable,
Yeah.
meaning you can literally draw a straight line, new curves, to perfectly split the classes without any overlap.
Yeah.
Well, the support vectors, they're those specific data points that are sitting right on the edges, the borders of this margin. I like to think of them as the guardrails, or maybe the critical anchors for that boundary.
Ah, okay.
They are the points that are closest to the separating hyperplane itself. They're quite literally the ones that support or define that decision boundary.
So these aren't just any old data points then, are they? From what I'm hearing, we're talking about the true heavy lifters here.
Yeah.
The crucial points that literally dictate where that separating line or plane ends up going. If you were to nudge one of these points, the whole boundary might shift. Sounds like they carry a lot of weight.
You've absolutely hit on a crucial point there.
Yeah.
Precisely. In what we call a hard margin SVM, that's the simple case we just described.
Okay.
These support vectors are actually the only points you need to figure out the margin itself and also the bias term, which kind of helps position the hyperplane correctly. And this is one of the most, well, brilliant and maybe surprising things about SVMs. Any other data points, the ones that are far away from the margin, nicely classified, they just don't influence the final separating boundary at all.
Really?
None at all.
Yeah.
None. You could literally remove them from your data set, and the SVM solution, that optimal hyperplane, would stay exactly the same. They just aren't critical to making the decision.
Wow, that's fascinating. So just think about the elegance there and the efficiency. If you're working with a huge data set, maybe millions of points,
Right.
but only, say, a handful are actually support vectors, your trained SVM model only needs to remember and calculate with those few critical points for making future predictions.
Exactly.
That's a massive win for computation, right? Both in training and especially when you go to use the model during inference. It makes the model really sparse in that sense.
It absolutely is. That sparseness is a huge, huge advantage. And that brings us nicely to takeaway number one. Support vectors are the crucial data points that define the margin and hyperplane in an SVM by being the closest points to that decision boundary. They are the essential few that literally support the classification, giving the algorithm its name and its incredible efficiency.
Okay, got it. But here's where, for me anyway, it gets really interesting and where the rubber meets the road between that sort of visual picture and the math underneath. While thinking of them as points on the border is super helpful, there's a deeper mathematical definition that clears up a lot of, well, potential confusion, especially when your data isn't perfectly separable. Because let's be honest, real-world data, it rarely ever comes perfectly clean like that.
Almost never.
Yeah, I remember when I was first really grappling with SVMs, this exact point about the math was where things finally clicked. Could you walk us through the Alfie stuff in a bit more detail?
I'd love to. Because what's truly fascinating here is that the real definition of a support vector, it lies deep inside the mathematical optimization process of an SVM. When we solve an SVM problem, we use a technique involving something called Lagrange multipliers.
Right.
These are usually written down using the Greek letter alpha with a little subscript I, so we often just say alpha.
Right.
Now, every single data point in your training set gets its own corresponding alpha value after you train the model.
Ah, the Elphi. I remember those vaguely from optimization theory. So what do these multipliers actually tell us about a specific point's role? Like, what's the practical upshot if a point has an alpha of 0? Does that mean we can just, like, forget about it after training?
The short answer is very elegant.
Okay.
The support vectors are precisely those data points for which their corresponding Lagrange multipliers, their alpha,
Yeah.
are not 0. They're positive.
Found 0.
Exactly. The weight vector, which is the mathematical thing that determines the orientation, the angle of our separating hyperplane, it's actually calculated as a sum. And this sum involves only these non-zero alpha terms multiplied by their class label, which is usually like made equal 1 or plus 1,
Yeah.
and the data point itself, the idleness.
Ah, I see.
So yes, absolutely. If a data point's alpha is 0, it means that point is correctly classified and it's sitting comfortably well outside the margin. It doesn't contribute at all to defining the boundary. Its presence or absence won't change the SVM's final answer. So yes, we can effectively forget about those points once the model is trained.
So the alpha isn't just like an on-off switch then. It's almost like a weight of influence for each point, telling us how much pull it has on where the hyperplane goes.
That's a great way to put it.
If alpha is 0, it's like that point has no leverage at all. That makes a lot of sense, intuitively.
Precisely. That's a perfect analogy. It really highlights which points are the active constraints in that optimization problem. And this isn't just some happy coincidence either. This elegant math connection is actually enforced by something called the Karuch-Kuhn-Tucker conditions, or KKT conditions for short.
KKT, right. Heard of those.
Yeah, they're fundamental principles in optimization. They essentially guarantee that when you're trying to find the best solution under certain constraints, like maximizing a margin, while keeping points on the right side, only the points that are actively kind of pushing against those boundaries will actually influence the final solution.
Huh.
They are the mathematical glue, if you like, that ensures only the relevant points end up mattering.
That's incredibly insightful. Knowing the why behind it through the KKT conditions really helps cement the concept. Okay. And that brings us neatly to takeaway number 2. Mathematically, support vectors are identified by their non-zero Lagrange multipliers, alpha, as these are the only points that directly influence the SVM's decision boundary and the weight vector that defines the hyperplane. If alpha is 0, the point is not a support vector and can be disregarded post-training.
Nicely put.
Now, let's tackle the scenario that I think causes most of the confusion when people are learning SVMs, and definitely where that simple points on the margin idea can lead you astray. We're talking about the CSVM, or soft margin SVMs.
The practical one.
Exactly. What happens when your data isn't perfectly separable? Or maybe you actually want to allow a little wiggle room for misclassification,
Sure.
maybe to get a model that generalizes better. Because let's face it, real-world data, rarely perfect separable clusters. What do we do then?
Right. This is where the concept of a support vector really expands beyond that initial very clean picture. In soft margin SVMs, we introduce something called slack variables. These are often written down using the Greek letter C. It looks a bit like a squiggly Z.
Yeah.
Zeta, exactly. These variables are essentially, think of them as penalties. They allow some data points to be inside the margin, or even worse, to be on the wrong side of the hyperplane, altogether meaning they're misclassified.
Okay, so we're allowing some errors.
We are. The optimization problem then tries to find this delicate balance. It wants to maximize the margin, keep that nice wide separation, but also minimize these slack variables, which really means minimizing the number and the degree of points that are either inside the margin or misclassified.
Okay, so here's the million-dollar question then. Are points that are inside the margin also considered support vectors in the soft margin case? Because I've definitely seen people get tripped up right here. They think only the points perfectly on the edge still count. This is where the nuance really kicks in, I think.
Absolutely. And that is a very common point of confusion. The answer is a definite yes.
Okay.
In soft margin SVMs, the set of support vectors definitely expands. We still look at the Lagrange multipliers, the alpha, to identify them, but how we interpret them broadens out. First, if an alpha is exactly 0, same as before, the point is correctly classified, it's sitting well outside the margin. It is not a support vector, irrelevant to the boundary.
Got it. 0 means out.
Right. Now, if an alpha is greater than 0 but less than C, And C is this really important regularization parameter.
The trade-off per net.
Exactly, the one that controls the trade-off between margin size and how much we penalize those slack variables.
Yeah.
If alpha is between 0 and C, then that point lies exactly on the margin. It is a support vector, just like in the simple hard margin case.
Okay, so on the margin still counts. Alpha between 0 and C. Makes sense.
Yep. And here's the key difference, the part that expands the definition. If an alpha is exactly equal to C,
Right at the limit.
right at that limit C, then the point is either inside the margin or it's actually misclassified. It's on the wrong side.
Okay.
In either of those crucial cases, inside the margin or misclassified, it is also considered a support vector.
Wow. Okay.
And this is why you might look at a trained SVM on some real-world data and see hundreds, maybe even thousands, of support vectors. It's because lots of points can fall into that inside the margin or misclassified category, and they still influence where the final boundary is drawn because their alpha is positive, specifically alpha equals C.
That makes so much more sense now. So the simple picture of points on the border holds for that theoretical hard margin case.
Right.
But for the much more practical soft margin SVM, the definition is broader. It includes points that are kind of struggling to be separated correctly, even if they're not perfectly on the margin line. Their struggle still informs where the boundary should go.
Exactly right.
And how we set that C value acts like a strategic dial then, controlling how much we care about those struggling points versus having a wider margin.
Exactly. Think of C not just as some abstract penalty, but as your strategic dial for managing that classic bias variance trade-off.
Okay.
A small C's value. It prioritizes a wider, maybe more general margin. It's willing to tolerate a few more misclassifications or points inside the margin, aiming for better performance on new, unseen data, less overfitting.
Right, more robust, maybe.
Potentially. A large C, on the other hand, is like a strict taskmaster. It punishes every misclassification or margin violation really heavily. This can lead to a narrower margin and a model that might fit the training data very well, but could potentially overfit.
I see. So understanding C is key to controlling which points become support vectors.
Absolutely crucial for real-world application. And the core point remains. The final solution, the hyperplane itself, still depends on all the data samples for which their alpha is greater than 0. Doesn't matter if they're perfectly on the margin, 0 alpha C, slightly inside the margin, alpha C, or even misclassified. All positive alphas mean the point is actively involved in shaping that decision boundary.
And what's really cool is that this whole idea, this mathematical definition using the alphas, holds true even when we use the famous kernel trick, right? For handling nonlinear data.
It absolutely does.
We're sort of projecting the data into a higher dimension where it becomes linearly separable, maybe?
Right, that's the magic.
But the support vectors are still those key points in that high-dimensional space, identified by their non-zero alphas, doing all the heavy lifting. It's such an elegant way to generalize the whole core idea.
It really is. The core principle remains remarkably robust, which is part of why SVMs are so powerful. And that brings us perfectly to takeaway number 3. In soft margin SVMs, support vectors include not only points that are exactly on the margin, where alpha C, but also those that are within the margin or even misclassified, where alpha C, provided their corresponding Lagrange multiplier is positive overall, alpha 0. This makes the concept much more robust and applicable for real-world, often messy, noisy data.
Fantastic. Okay, let's quickly recap the ground we've covered, summarizing what we've discovered about support vectors and SVMs. This should really help you cut through any confusion and lock down this core concept.
Sounds good. First, takeaway number 1. Support vectors are the crucial data points that define the margin and hyperplane in an SVM by being the closest points to that decision boundary. They're the essential points that literally support the classification, and they drive model's efficiency.
Right. And takeaway number 2. Mathematically, the definitive way to identify support vectors is by their non-zero Lagrange multipliers, those alpha values. These are the only points that directly influence the SVM's decision boundary and the weight vector defining the hyperplane. If alpha is 0, the point is not a support vector and can be safely ignored after training.
Perfect. And finally, takeaway number 3. In soft margin SVMs, which you'll encounter most often in practice with real data, the definition expands. Support vectors include not only points exactly on the margin, 0 alpha C, but also those within the margin or even misclassified points, alpha C, as long as their Lagrange multiplier is positive, alpha 0. This allows SVMs to handle complex, noisy data by balancing that margin maximization goal with classification errors.
Excellent summary. So Thinking about all this, if support vectors are truly the important data points, the ones that define the entire decision boundary, what does that imply about the, say, the robustness of an SVM model if these specific support vector points happen to be noisy, or maybe they're outliers in your data set?
That's a great point.
It really highlights where the model gets its strength from these critical points, but maybe also where its potential vulnerabilities might lie, doesn't it? If your crucial support points are themselves unreliable or unrepresentative, what does that actually mean for how your model will perform on new, unseen data? It's definitely something to consider as you build and deploy these powerful tools. Maybe you need to think about things like outlier detection beforehand, or look into more robust variations of SVMs to guard against that kind of issue.
That's a really insightful thought to leave people with.
Yeah.
It drives home that even in a highly efficient, mathematically elegant model like an SVM, the quality and the integrity of those critical data points, the support vectors, are absolutely paramount. It's not just about the algorithm. It's profoundly about the data it learns from, especially the data right there at its decision boundaries.
Exactly. That's the kind of deeper understanding we aim for in these deep dives.
That's all for now, folks. Please like, share, and subscribe for more like this.